you very much. So Steve and I have agreed to split these talks according to spin and charge, even though, of course, everybody knows spin and charge are a couple in these materials. So it will be somewhat artificial, and I hope Steve won't mind if I mention the word spin once or twice in my talk as well. Okay, so since the summer school, I will give an introduction, fairly elementary pedagogical introduction of what we mean by charge density wave, charge order, in elemental or simple metals and in transition metal oxides. I will then sort of summarize many aspects certainly comprehensively of our current knowledge of two-dimensional charge order in these materials. And then I will also discuss more recent work on three-dimensional charge order in yttrium-invariant copper-oxide and its response to strain, uniaxial and biaxial epitaxial strain. And maybe in the end, light exposure if time permits. Okay, so like everybody else, I'd like to acknowledge my collaborators. I won't go through the whole list. Actually, I won't mention many people at all, except for a few students here who know Kim, Martin Bluschke, who did some present X-ray scattering work. They played key roles in these data that I'll present. Mathilde Dacon, who used to be my group, is now at KEIMER. Ying Peng, she was a postdoc with Giacomo Kelly. She's now in Peking University. Alex Franio, my student, is now at UC San Diego on the faculty. And then I'd like to stress also a very fruitful collaboration we have with Andy McKenzie's group in Dresden, another Max Planck Institute, and his student Mark Barber and Cliff Hicks, his group leader, as well as people at our institute are growing thin films by WCO. And since I mentioned this collaboration with Andy McKenzie, let me just give you a very 2-second plug-in. We have just started a new graduate program. We're just recruiting for students that run across several Max Planck Institutes in the Max Planck Society. Here's a website. We also have some external members. Seamus actually is a member of this new center. There's a website for more information. And please don't hesitate to contact me if you're interested in, or your friends are interested in joining us in this graduate center. Anyway, so this is sort of going back to the beginning of charge density waves, beginning with the Piles distortion that I believe most people in the audience will know about. So this is a simple cartoon here of a one-dimensional metal with uniform charge density that is unstable to lattice distortion with periodicity, the Fermi wave vector that introduces a gap at the Fermi level and lowers the overall kinetic energy of electrons. You can detect this charge density wave if you measure superstructure peaks in X-ray or neutron diffraction. That will be in general incommensurate with the underlying lattice because the Fermi wave vector is incommensurate. But you can also look at phonons that, in the presence of a non-zero electron-phonon interaction, will show so-called cone anomalies that will reflect the electronic susceptibility, which will be particularly large, of course, of this wave vector, and that introduces dispersion anomalies. There's a corresponding anomaly in the line width of the phonons via phonic transformations, and these anomalies will be particularly strong, of course, in 1 dimension, and weaker in 2, and even weaker in 3 dimensions, because of these with momentum space averaging in 2 and 3 dimensions. Okay, so that's basically the work of Piles, I believe, in the 1930s. Over the years, these kinds of effects have been verified in a number of different materials. There's a lot of work on this in the 1970s. This is one particular paper I select from David Monckton, who studied tantalum diselenide, which is a two-dimensional metal. He saw by X-ray diffraction these incommensurate peaks. Actually, in this material, they happen to be commensurate, 1/3, but in general, in these glass materials, they're incommensurate. You see them coming up below this charge density transition. And he also studied phonons, and this is one particular acoustic phonon branch where you see a prominent anomaly at the charge density wave factor. Actually, this anomaly happens even at room temperature, much above the actual three-dimensional charge density transition, as you might expect in the low-dimensional material. Okay, so this is sort of ancient history. More recently, people have actually gone back to these materials. This is some more recent work by Frank Weber and Dimitri Resonant at KIT, who studied niobium diselenide. Again, by neutron scattering, they found, again, these big cone anomalies. And they noticed that these cone anomalies are actually quite extended in momentum space. And then there were some theorists who were actually doing some calculations, LDA calculations, looking at the joint density states for these electronic transitions used by phonons. What they found was actually that there's actually no prominent peak in the electronic susceptibility at this charge density wave factor, even though there is a large anomaly in line width, even in LDA. So they could reproduce these cone anomalies, but then they realize, or they argue, that the standard picture of nesting, which I just showed you in the Pyle's work, is not what's really causing the charge density wave of these materials, but rather this wave vector of the charge density wave is really determined not so much by the electronic nesting or electronic susceptibility anomaly, but rather by the electron phonon interaction. So that's a message I'd like you to remember also for our discussion of charge density waves and CUPRATEs. Okay.
Is there a material where it is actually looking like classic nesting?
Yeah, there's one-dimensional material that show much more pronounced cone anomaly, the so-called Krogman salts. Right? I didn't bring the data here, but they seem to be more in this.
Not in 2D, not among 2D materials.
I'm not aware of the 2D materials where this picture, nesting-induced instability, is really very realized in a sort of textbook fashion.
But this could not account for commensurate CDW.
Yeah, so for commensurate, of course, you need to have some locking effects.
Exactly.
Yeah, that's true. So, so that's sort of one paradigm for charge order, right, in materials where you have, a weakly, interacting metal, right, and everything is sort of electronic kinetic energy, no correlations at all. In the opposite extreme, the opposite paradigm, if you're looking at transition metal oxides where the charge is localized, in particular metal ions, and there's a lot of transition metals that are stable in different valence states, right? We have listed two. Most prominent is perhaps the manganites, where you have stable 3+ and 4+ ions, and you have compounds based exclusively, of course, on 3+ and 4+ valence states. But then when you start varying the electron density here by chemical substitution, you're going from one limit to the other, right? So you're going from 3+ compound, lanthanum MnO3, all the way to strontium MnO3, which is based on manganese 4+. And when you go, when you're somewhere in between, you tend to get sort of ordered patterns of these two valence states. This is a very common kind of situation in transition metal oxides. You also have this cobaltates, the nickelates, etc., etc. And this kind of situation happens And here, because you have these ionic valence states that are stable, or people sort of look at it in real space rather than momentum space, and most often these kinds of states are commensurate, right? Clearly, because you have these ionic configurations that are particularly stable. If you have incommensurate, you go to different kinds of configurations that are then not as stable. And often, not always, but often, these kinds of charge-ordered states are also associated with magnetism. So kind of magnetism is then also modulated because the length of the magnetic moment on length 3 plus different lengths. Okay, so this kind of charge ordering is then often referred to as charge order, and this Peierls state is often referred to as charge density wave order. But both terms are not rigorously defined, and of course there's a continuum in between. Right? Anyway, so this is sort of these are sort of two paradigms that are of relevance in discussing charge overalls and cuprates. And
here, would you see multiple Qs because you want to have rather sharp charge density?
Yes, you can have multiple harmonics. Yes, yes.
As opposed to
that has also been seen. So you have multiple harmonics. It's not a sine wave, it's a square wave. Okay? So that's true. Often these are, however, washed out because of disorder. If you have any kind of disorder in such a state, the first thing that goes away is the harmonics. They're much more sensitive to this. Anyway, so this is sort of common law in transition metal oxide physics, and when the first evidence of charge order appears in the cuprates, people were naturally using this kind of picture. So this is a generic cuprate phase diagram that you've seen many times, of course, in this summer school. So you have two thermodynamic phases, D-wave superconductivity and antiferromagnetism. But even very early on, people noticed that there's sort of a dip in the superconducting TC at moderate doping, and this is where John Tranquater found in this material, this lanthanum-based material, evidence of this commensurate charge order. Actually, the first thing that we saw was actually magnetic superstructure with periodicity 8 unit cells. Okay, so this is these are the corresponding superstructure peaks that have this periodicity of Q vector 1/8. Later, when people look more carefully, they actually realize that these are not truly commensurate; they're also slightly incommensurate. Okay, but at that time, 1995, when Tranquater found these peaks, he thought they were commensurate. And there's a charge modulation. Actually, he sees the neutron scan. He doesn't see the charge directly, but he sees the response of the lattice to this charge modulation with the 4 units of periodicity. Right? So these commensurate order, and with transition metal oxide, so quite reasonably, he and others discussed this in terms of the real space picture here. And this is sort of a picture that was published in this milestone paper, now referred to as stripes. Okay, and the way this was discussed at that time, and still is being discussed in this way, is in terms of a sort of realization of nanoscale phase separation. Right, so you have a small density of holes that you want to add to this antiferromagnet. Right, and these holes, of course, when they delocalize, they will break antiferromagnetic bonds. That would cost some energy, right? But if you arrange these domains in this fashion here, where you have sort of rivers of so-called rivers of charge that are not magnetically ordered, the electrons can delocalize along these one-dimensional lines without having to break any magnetic bonds. So this was supposed to be favorable from the point of view of electron kinetic energy and the exchange energy in the system. right? And what John Drinkwater realized, even at that time, but he and others have followed up later on, was that this kind of stripe order is really competing very strongly with superconductivity. Even in this system, this is the original Bates-Lawrence-Miller compound, where ITC superconductivity was first reported, even to the extent of almost completely suppressing superconductivity at this 1/8 doping. Okay? So static stripe order is really competing very strongly with superconductivity. Now later, of course, people were looking for this type of ordered state also in other cuprates to see whether this is a generic phenomenon. But it turned out that this type of stripe with coexisting spin and charge order is really almost exclusively seen in the lanthanum-based cuprates. Okay, so in other cuprates like Bisco, that was mentioned already, also in YBCO that was mentioned. If you look at moderate doping, you don't see this incommensurate magnetic order. Right? So this type of stripe state was soon realized to be a peculiar phenomenon for this kind of cuprate, this particular cuprate family. And well, it's now known why this stripe order is particularly stable in this family. This is because there's some soft tilting modes. So here you have actual octahedra here of oxygen surrounding the copper, and these octahedra can easily tilt in different directions. And some of these tilt directions actually have propagation vectors that coincide with the favored periodicity of the stripe order, and therefore it's these tilt rotations are actually favored stripe order. Like when you look at YBCO, for instance, you don't have octahedra, you have tetrahedra that are not easily tiltable. Right? So so you have these different phases here: low temperature orthorhombic, low temperature tetraangular, where these octahedra tilt in different directions, and these are also marked here on this phase diagram. Right? LTLO, so the LTO, etc. They are different types of tilt order phases. Okay? So this type of phase is really not generic to the cuprates. What is generic, however, is charge order. That is now seen basically in every cuprate, and there's over the years there's been a lot of evidence for charge order, beginning perhaps with this famous checkerboard and vortex course of this, I think, business 2212 by Jenny Hawken and James Davis. Well, Seamus has already shown this, so I don't have to dwell on that. I just wanted to point out that in these vortex cores you have charge order, but you don't have magnetic order. Right? So in contrast to the stripe phase in the 1900 cuprates. Okay, and Seamus also showed this picture here, a detailed picture of one of those charge ordered states, where you see copper atoms here marked by crosses, and the charge is actually piling up in between the copper atoms on the oxygen atoms. And that is, this type of finding is simulated some work, theoretical work, then in the framework of TJ model. This is some work, for instance, by Feuchter and Sachdev from the late 1990s, where they've looked at the phase diagram of the extended TJ model and found lots of these sort of valence bond solid phases with dimers lined up in some regular pattern, and each dimer corresponds to a spin singlet state, right? So, but this is kind of this is unique to the cuprates. That doesn't happen in the manganites, for instance. This spin singlet formation, because there you don't have spin 1/2. In the cuprates, spins up 1/2, so they can easily form singlets with the neighboring spin ones. And these singlet pairs can then form different superstructures. Okay? But they will be non-magnetic. Right? So this bond order will then be realized without coexisting magnetic order. So that's one model for charge order of the cuprates that is more generic than the original strike picture of Tranquora. Okay, so now let me just switch to some of the more recent work on YBCO. Right, so these observations here of charge order vortex cores, they were also, of course, registered by the community, but it wasn't really realized how universal this kind of charge order was until the recent work 6 or 7 years ago on the YBCO system, which in many ways is a prototypical high TC superconductor. It has high PC, 93 Kelvin maximum, and it's exceptionally clean because all the dopant atoms that in the 214 viscose system are added by chemical substitution and random substitutions. All the dopant atoms here are lined in chains, right? And the chains can be, if you take care, can be made more than 100 angstrom in length. So that means you have minimal disorder. And of course, disorder in most other cuprates is really a tremendous complication because you don't really realize to what extent the phenomena that you see, especially regarding different charge configurations, are actually induced by the impurities in the system. Okay, so the manifestation of this minimal disorder in the YBCO system the quantum oscillation that Cyril has already discussed, that you see even in underdoped. So in overdoped materials, several families exhibit these quantum oscillations, which are very sensitive, of course, to impurities. But this paper here, published by Fair's group, was the first actually demonstrated quantum oscillations in underdoped systems. Now, there are a couple of other cuprate families where this is also being observed. Okay, so this is a manifestation of particularly minimal disorder. Okay, but even in this system, let me just show you this this picture of reciprocal space that we published with Mathieu 5 years ago. Where you see that even in this very clean system, reciprocal space is full of diffuse scattering from oxygen disorder. Right? This is not one of the cleanest samples here, where these peaks are sharper. But when you go to a generic YBCO crystal here with X not in a particularly favorable value, you see these huge diffuse scattering peaks. And that, on the background of these diffuse scattering features, is very difficult to actually identify electronic charge order. We were talking at lunch with and she was offering to let a machine learning algorithm look at some of these data. But I think, at least at that time, we didn't have a neural network that could analyze the data, so we had to actually study them ourselves. And so it was really quite difficult to then go and say, oh, this thing here, that's charge order, right? Because most of these features actually come from oxygen defects. Anyway, so tremendous advance in the field was really made possible by the invention of resonant inelastic X-ray scattering, where you actually highlight particular X-ray diffraction peaks or X-ray diffraction features by tuning your X-ray photons to a resonance of the particular element you're interested in. And this is copper in our particular case. So So the way this works is, we're using a photon that's tuned to this L absorption resonance, so that promotes a 2p core electron to the 3d Lagrange shell. And then, depending on particular polarization configurations, the spin-orbit coupling in this intermediate state can actually flip the spin, so you can use a spin excitation. You can, but you don't have to use a spin excitation, and then you're probing the spin flip excitation in the state that you're generating here. Okay, so you can both you can then develop a formalism for this Rix technique, Rix cross section, and it turns out that this is quite analogous to neutron scattering. You can actually write the cross section in terms of the dynamical susceptibility that you also see in neutron scattering, and then you can write for the Rix operator an expansion that includes then the X-ray polarization state in the initial state and the final state, and then you can get different terms depending on the relative orientation of the incident and scattered photon polarization. In general, for generic materials, this is actually can be quite complicated depending on your crystal symmetry. For the CUPRATEs, however, because you only have one particular orbital, often in manganites, for instance, you get spin, charge, and orbital excitations. In the CUPRATEs, all the low energy orbital degrees are frozen out, and you only have these spin and charge excitations that you can select by manipulating your incident and final photon polarization. Okay, so if you're cross polarization, you look at spin excitations. If you're parallel polarization, you can charge excitations. Okay, and this is what we're doing here. We don't really control the final. Yes.
On the previous slide, I just have a little quick question. Yeah. So this sigma 2, that term.
Yes.
That would be able to measure the two spin flip excitation, right?
Yes. Yes.
SS
yes.
and then the other part.
Right. That could also. That's true. Anyway, so we don't usually analyze the final polarization. We've started doing this, but often this is not done. But still, just by looking at the dependence of the Rix cross section on the initial photon configuration, we can discriminate between spin and charge excitations. And this was the first evidence of charge ordering in yttrium-bearing copper oxide. That was sort of parasitic to an experiment we were doing on spin excitations. So this is a full spectrum here running from 0 to 4 electron volts that shows these PD or interband transitions here at high energies, and you see the spin excitations that Stephen will discuss in the next talk. But then in the elastic channel, you also see this huge peak that could be identified as coming from charge ordering based on the polarization dependence of this of the cross section. And this, this charge peak happens to be at an incommensurate Q. It's close to 1/3, but it's very clearly not 1/3. And based on the symmetry of the reciprocal space, so it could be identified as a generic charge ordering, charge ordered state in the copper oxide planes. Because we, after all, we're looking at phenomena that are related to the copper atoms in the copper plane. The chain atoms actually have different resonance conditions. And I will come back to that a little later. Parallel to these experiments that we did with resonant X-ray scattering, Steve and Yuan Chang and others had forward and also used hard X-rays to find the same phenomenon. And previously, as Cyril had pointed out already, Marc-Henri Julien had found evidence for charge ordering in high magnetic fields in YBCO. These papers here, although they could not identify the ordering wave vector. Okay, so this was established even in this material, YBCO, which many people regard as the E. coli of CUPRATE superconductors, that charge ordering actually exists. So there are, again, these two ways of looking at the charge order, either in real space or momentum space. Now, here the ordering wave vector is incommensurate, so it makes more sense actually to look, what kind of momentum space features this could correspond to, this charge ordering wave vector. And it turns out that the wave vector of the charge order is close to the spanning vector of the Fermi surfaces here in adjacent Lorentz zones. Okay, so it's at least in the right direction, and I'll say something about the length in a moment. But if you had a charge density wave that formed in these segments of the precipitate space, it's clear already that it would compete quite strongly with superconductivity, because this is also where the superconducting gap is maximum. Okay, and this is indeed what happens. Well, before highlighting the competition with superconductivity, let me just remind you. I don't have to really go into any details, but just remind you about some of what Cyril has said. If there were a charge density wave with this wave vector, it would actually give an explanation for the formation of electron pockets through the associated Fermi surface reconstruction. And you see these electron pockets in the quantum oscillations, and charge density wave reconstruction gives you electron pockets of roughly the right size, as he and Suchitra and Sebastian have shown. And of course, they also explain why the Hall effect is negative in these Hall-Doped cuprates at low temperatures. And stimulated by this discovery of the charge density wave order in YBCO, a lot of theorists have actually looked at this Fermi surface here, the whole-line Fermi surface, and tried to see whether magnetic interactions could actually lead to formation of a charge density wave, just like in these TJ model calculations I showed you earlier, but now based on a sort of realistic Fermi surface with magnetic interactions. And they found out quite early that yes, such a charge modulation could actually be stabilized, but at least initially it seemed like the dominant instability would be not in the bond order, the copper-oxide bond direction, but 45 degrees from this. But then, some follow-up work by Andrew Chilcott, who used to be here, and others, established some mechanisms that could also stabilize a charge density wave vector in the copper-oxide bond direction. Okay. Now, I already mentioned the competition with superconductivity, which you can see immediately by looking at the temperature dependence of these charge density wave features. Okay, so there's, when you look at the temperature dependence, you see that there's a gradual onset here of charge order at around 150 Kelvin, which is actually below the supergap temperature in this doping range. And then, the intensity grows gradually, and as you might expect for instability that actually goes critical, but before it actually goes critical, before the correlation length completely diverges, superconductivity happens, and at the superconducting transition, the correlation length and intensity actually drops precipitously. So that tells you right away about any models that charge order competes against superconductivity. Okay? So there's actually this cusp here at TC, and when you look at Landau-Ginzburg-Landau models. It's actually not so easy to reproduce this kind of cusp in an autoparameter temperature dependence, and now it was work both by Sarstedt but also by Kathleen and her collaborators, trying to describe this behavior in terms of sort of fluctuations of a higher dimension autoparameter that is composed of both the D-wave superconductivity and the charge density wave autoparameter. And there's some success, as you can see in this plot here. So we were actually able to describe the cusp at TC, but you see both at high temperatures and low temperatures there's significant deviations, which might then indicate mechanisms that go beyond this pure electronic mechanism that we were discussing, and perhaps also include component interactions and disorder, which is also quite relevant as you will see in a moment. Here's another evidence of competition with superconductivity that was first pointed out by Chang and Hayden and their collaborators. What they did is they studied the charge density wave intensity as a function of magnetic field. Above TC, magnetic field doesn't do very much to the intensity, but below TC, you see a pronounced magnetic field dependence, which you can also attribute to the competition between superconductivity and charge density wave order. The magnetic field, of course, destabilizes superconductivity by orbital depairing, and if the charge density wave is comparatively unaffected, it will then gain relative to the superconductor and be strengthened by the magnetic field. Okay, now so far this was mostly done at one doping level. If you study the doping dependence of the charge density wave, it turns out that in YBCO and in most other materials that have so far been studied, the wave vector here goes down as a function of increasing doping, which is what you expect if this is really a spanning vector of the Fermi surface, because then the Fermi surfaces expand with increasing doping, and this vector becomes shorter. Okay? Now in the mantle-based superconductors, you actually see the opposite behavior. And this is no doubt a consequence of the fact that you're now dealing with stripe order here, magnetic, and a charge component. And recently there's been some work actually elucidating the wave vector of spin and charge density waves in this material. This is by Mark Dean's group at Brookhaven, who looked at both spin and charge density wave in the same material. And they found that actually there's a lock-in between the two at a particular temperature here. And this kind of lock-in, the interference between spin and charge density instabilities, that goes a long way towards explaining the different behavior of the wave vector doping dependence in this family of materials. Okay, now I showed you this cartoon several times, right? But you should realize that this cannot be literally true, because here in the underdoped materials, you actually have the pseudo gap that leads to gaps here at the antinodal regions at the Fermi surface. There's actually no states that could be nested here. Rather, the states are related. The states at the Fermi level are concentrated in these Fermi arcs. And indeed, when you look at the Fermi arcs, now not YBCO, but a bismuth-based superconductor, and study the charge density wave in the same material, you realize that it's not really this wave vector here that connects the unrenormalized Fermi surface. It's really the wave vector connecting the Fermi arcs that is characteristic of the charge density wave of these materials. So this is not inconsistent. The charge density wave interpretation is not inconsistent with the with the common knowledge of fermiology. Yes? Mm-hmm.
So if you look at, for example, Visco 2201 there, and you look at that connecting wave vector, matching the tips of the arcs, of course, I completely agree with that. But that's not consistent with the charge density wave, because there's no gap.
Okay, so that's, okay. If you had a truly long-range ordered charge density wave, you would, of course, see a gap here, right? And that's not the case, right? So things are certainly more complex, right? So it's not like a standard charge density. You just superpose this piles-like picture here on this Fermi arc fermiology. That's not what happens, right? So there's a more complex interplay between whatever causes the Fermi arc and the charge density. Yes?
And also some of the RPAS data clearly indicates that there is temperature dependence to the length of the Fermi arc.
Yeah.
Of course, you could take the lowest temperatures or something, but then it would seem like this spanning vector would also be temperature dependent, for which there's absolutely no evidence.
That's good, yes. So clearly, I mean, this is you should take this as an empirical observation, right? But in the microscopic physics behind this, this apparent similarity between the wave vector connecting the Fermi arcs and the charge density of physics is still not really understood. And there's also even some uncertainty in the definition exactly what you mean by this wave vector. There's certainly quite a large systematic error bar, on top of the error bar that you get with the experimental error bars that you find in both the photon emission and the X-ray scanning. So this is sort of a phenomenological observation, right? But there's still some work to be done to see what the mechanisms, underlying mechanisms should be. Yes. Right. Okay. So this is sort of the phenomenology of the charge density wave itself. So we already in the last talk we heard a little bit about electron-phonon interaction, and over many years, people like Machovius and Resnick and even Lee had studied phonon anomalies in these materials. In hindsight, it turns out that all these phonon anomalies really concentrated around the charge density wave. So you look at Machovius data here, it's 0.3. Here, our data on the bond bending. This is the bond stretching mode. CUPRATE, the bond bending mode, also has this very pronounced cone anomaly, and all of this can be now associated with the charge density wave phenomenon. Not with the temperature dependence, everything is consistent. And when you then look at so these are sort of generic phonons that are present in every CUPRATE. Bond bending, copper-oxide bond bending, and bond stretching mode are present in every CUPRATE, but they're also very pronounced, very sharp anomalies in lower lying optical and even acoustic modes. They are not generic to the CUPRATE. So many phonons exhibit pronounced cone anomalies. At the charge density wave vector, and these anomalies can be quite strong, right? If you look, for instance, here at the energy of this mode here, let's say this mode, it's 8 MeV, and the line width here is let's see, the line width is 4 MeV, right? So this phonon is really critically damped. So these are very large anomalies. So surely, when you're considering the energetics of the charge density wave, these have to be taken into account. So the electron-phonon interaction cannot be ignored. So this is something that is not part of the initial work in the charge density wave, but if you now want to get a better understanding of the charge density wave, then you need to also considered electron-phonon interaction. But of course, this electron-phonon coupling favors the charge density wave which competes against superconductivity. So this should not be mistaken for evidence that the phonons actually enhance superconductivity. It's rather the opposite. That's what I think about this. That's how I think about this data. We also then look at the same kind of data. So these are phonons here we were studying. We also see here at zero energy an anomaly at the charge density wave vector. Okay, so this is now looking here at this temperature dependence, but in an energy resolved way. And you find that this charge density wave peak is actually perfectly sharp in energy. Right? So initially we were thinking, well, these are fluctuations, and they're certainly fluctuating components here. So with this initial resonant X-ray scattering work, we sort of integrated over quite some energy, about 100 MeV, that's our energy resolution. Now we have an energy resolution of 1 MeV or so of these data, and we still see charge density wave peak. That is, however, broad in momentum space. So these are this is static short-range order, charge density wave order. So that means that we have sort of nano domains that are static and very likely were created by defects in the system. So even though YDCO material is not perfect, as you saw in this diffuse scattering max, there's all evidence of disorder, derivative, as hard as you can try. And these charge density wave domains that are established around 150 Kelvin or so, they're suppressed in the superconducting state, but they still remain in the superconducting state. So you have inhomogeneous coexistence between charge density wave order and superconductivity. Right? Even in this very clean, relatively clean superconductor. Never get rid of the inhomogeneity. That's the so-called central peak phenomenon. It's also known from previous work on strengths titanium, for instance. Okay, now following up on this work, there's a lot of, basically all families, even the electron-doped materials, have been investigated by resonant X-ray scattering. And you see, charge order at this way, all around this wave vector, all of these materials. So this is really a universal feature of the copper-oxide, even though, and they're all in the same direction, always in the copper-oxide bond direction. But the width here of these peaks differs quite strongly from one material to the other. So in YBCO, these peaks are particularly sharp, probably reflecting, at least in part, the low level of chemical disorder in these materials. But it may also be that specific aspects of electron-phonon interaction will then enhance or be more or less favorable for charge order in these different families of materials. But in any case, if you want to draw now a universal phase diagram through the CUPRATE, as we try to do in this review article here, charge order is certainly going to have to be part of it, right? And for this here, we have this dashed line, we say charge order, but we should keep in mind that this is never really long-range order, right? So it's always short-range order that we're talking about, with a gradual onset here, at around 150 Kelvin, well below the pseudo-gap. So this is an instability in the pseudo-gap regime, but it doesn't cause the pseudo-gap. Okay, and now, this was sort of the situation until last year. But then, Giacomo Giuliani and Ying Peng, and we were also participating, sort of said, they didn't really care about any theories that have been proposed where charge order is supposed to be stabilized by magnetic fluctuation. They just kept on going, looking for these charge density wave peaks as a function of doping. And then, in this material, bismuth 2-1, and the initial data seem to suggest that the charge order is only present in the underdoped range, because then when you go to optimum doping, the charge order disappears. But then they realized that when you go even further, well into the overdoped regime, you again saw charge density wave peaks. This is resonant X-ray scattering, so these are resonant at the copper absorption edge. These are not so random superstructure peaks. They're really, they look like the charge density wave peaks in the underdoped regime. You can then even track the Q vector and the overdoped state here. So the trend that you see from the underdoped state as a function of doping continuous. And the intensity, when you look at the intensity of these peaks, they're actually more intense than in the underdoped state. And there's a sharp peak in intensity here at the so-called Lifshitz point, where you see I don't have it here, but in the photo emission data, these were studied simultaneously with photo emission. You see that there's the whole light Fermi surface transforms into a direct light propagation. Right? So this is Van Hoff's famous Van Hoff singularity, where you see this charge order now being maximum again. Right? And when you then look at the temperature dependence, so this is manifestly outside the superconductor regime. Well in the overall state, yes? James?
There's no gap on the 2201 Fermi surface anywhere.
Okay, I'll come to that on the next slide. When you then look at the temperature evolution, right, you see this peak broaden, just like it does in MCO, but the integrated intensity is really almost temperature independent, like the room temperature. So this is really exceptionally robust charge order, well outside the superconductor regime. Right, with a correlation length of at least 50 angstroms. That's even longer than in YUCO. Now about the gap, of course you would expect. Regimes disappeared? Yeah. Okay. Anyway, I will tell you a bit about the interpretation. Of course, near the Lifshitz point, you might expect enhanced density states, and that is favorable for charge density formation. But as James pointed out, you would expect a gap there in the Fermi surface reconstruction. However, when you look at predictions of this Fermi surface reconstruction, this is actually very subtle. So it may be washed out by this order, or people who work in photo emission work. But there's also an alternative scenario in which this charge density formation is not actually associated with the Fermi surface at all, but the wave vector is really characteristic of some kind of frustrated phase separation. It's more like a stripe-like picture where this what we call charge density wave vector is actually interpreted as a periodicity of this phase separation. Right? You have a periodic phase distribution, and this is the characteristic wave vector connecting this. So in that scenario, you would not actually expect any gap at the Fermi surface. Okay, so this interpretation of this charge density wave-like phenomenon in the overdoped state is still under debate. Okay, so I have a few minutes left. Let me now talk about this segment of the phase diagram, which is marked by this hashed area here, and that indicates three-dimensional charge order in high magnetic fields. Okay, so there was already some evidence for long-range charge density order from quantum oscillations, because you need large disorder-free regions to close the cyclotron orbits to give rise to charge to these quantum oscillations. But the first evidence that three-dimensional charge order exists in high magnetic fields was given in this paper here by Arisha and Lee's group at Stanford University. They studied YBCO in pulse magnetic fields up to about 30 Tesla, 28 Tesla, at the LCLS, which is a pulse X-ray source. And what they found is, on top of this, I should explain, this is the momentum transfer perpendicular to the copper-oxide layers. And for two-dimensional charge order, you wouldn't see any dependence of the intensity on this direction perpendicular to the layer, right? With a grain of salt, because you have correlations with the tiny unit. Okay, so that's a scattering rod corresponding to two-dimensional order. But what they saw in high magnetic fields was, on top of this scattering rod, also a Bragg peak that came up at around maybe 20 teslas. Okay? And this Bragg peak in the plane, this is the in-plane momentum, has the same velocity, the same Q vector as the two-dimensional charge order. But it's a true Bragg reflection, with order in 3 dimensions. Okay? So that has motivated us to take advantage of the technique that Andy Mackenzie has developed. His group to study strontium gluconate, for instance, Lifshitz transition to strontium gluconate. He adapted this technique, these 2 students here adapted this technique for X-ray scattering so that we can also work in transmission. Now studied the same phenomenon here. Charge density wave as a function of momentum transfer perpendicular to the copper-oxide layers and within the copper-oxide layers as a function of strain, uniaxial strain, right, up to about 1%. Okay, and what we found is that so we reproduced the two-dimensional charge order in the absence of strain, but when the strain reaches about 1%, a huge Bragg reflection comes up. Okay, that's even sharper than in the high magnetic field experiments. So it indicates correlation length exceeding hundreds of angstroms. Okay, so just by application of strain in the right direction, you can stabilize three-dimensional long-range order. And the most amazing thing is actually
the momentum is outer plane momentum. Is that the same?
No, the outer plane is just repeating every unit cell. So that's the same periodicity as the crystal structure. Right? So it's commensurate with the crystal structure. Whereas the in-plane periodicity is incommensurate, matching the periodicity of the two-dimensional structure that had already been known. The most amazing thing that I find here in this data is that the very strong competition with superconductivity. So this Bragg peak here can be monitored as a function of temperature, has an onset around 100 Kelvin or so. It then goes up very, very strongly and it drops down to 0 here in the superconducting state. So there's no residue of the intensity that you see in the two-dimensional charge order. Like I showed you before, this doesn't go to 0. There's always some homogeneous coexistence, but this three-dimensional charge order is really a genuine thermodynamic competitor with the high TC superconducting. So in the D-wave superconducting state, this normally disappears completely.
Could the strain lower the TC then?
Yes, a little bit. But so not 10 times.
So what disappears is the Z direction, the periodicity in Z direction, or the charge order completely disappears?
No. This okay. So this is I only show the temperature dependence, but as a function of strain, the two-dimensional the rod is only weakly affected. It's somewhat enhanced, but not strongly. But this peak here is very strongly enhanced. So the 2D charge order is not very strongly affected by it. It does its regular thing, sort of by strain. But the 3D charge order is extremely strong.
And when it goes superconducting, only the 3D one disappears, but the 2D one stays.
Yes, exactly. So that's actually shown here, in the superconducting state at finite strain, right? So here at 24 Kelvin, this peak is completely gone, but the rod, which is modulated due to this intra-binary correlations, is still there. Okay, so let's skip over the phonon anomalies here. You also see a soft phonon that drives this charge order. The final thing I'd like to show is some recent work done by the student Martin Bluschko, who's just graduating on just ordinary YBCO films, where he put films on different substrates, including standard substrate STO, and found the regular 2D charge order here, just as in the simple crystals. But then, even in the absence of uniaxial strain on magnetic fields, he also sees a Bragg reflection characteristic of three-dimensional charge order. Okay? So on top of the 2D charge order, we see this 3D charge order. And this 3D charge order is again, just like in the overdose bismuth 221, it has the same periodicity, right, as you can see here. So it's this same phenomenon that gives rise to 3D charge order as the 2D charge order. But the 2D charge order does exactly the same thing, with the cusped TC as in the single crystals, but the 3D charge order is actually stable up to room temperature. So it is 300 Kelvin. So this charge order can be extremely robust, right, under the right conditions. And it also doesn't show any kind of anomaly at TC. So that probably means that it's somehow phase separated from superconducting regions. In which way we don't know. We will study this with micro-diffraction, etc. Maybe the last thing I'd like to show. I think I'm coming to the end. I have lots of other things to show, but let me just show this thing, which is now resonant scattering. This is resonant X-ray scattering from 3D charge order in these YBCO films. And what you see here is three different features here as a function of photon energy, right? So for the 2D charge order, I told you that it resonates at the energy characteristic of in-plane coppers, right? Then you have here a peak that's characteristic of oxygen order in these materials, and the oxygen order is happening in the chains, right? So this ortho-2 chain order protection resonates at the energy that's characteristic of the copper-oxide chain atoms, right? So these are two different resonance energies. So we can site-selective resonant X-ray scattering. And this 3D charge order actually has both components. So both the chains and the planes are participating. Right? So the chains in the YBCO structure participate in the three-dimensional charge order. They communicate information between the copper-oxide planes, and that may be the reason why this three-dimensional charge order state is particularly stable in the YBCO structure. Okay, so let me just summarize. This part of the talk, you can stabilize actually three-dimensional charge order on top of the magnetic field dependence that was previously known by uniaxial strain. We can also grow it epitaxially on strontium titanate, which is nearly tetragonal as a substrate, and then I didn't show you it, but we can also stabilize it by illuminating crystals with polarized light. Okay, so we can modify a big plane. Just some thoughts on the mechanism of why is 3D charge order stable in these films and not in the crystals. Well, one mechanism that may contribute is that the substrate is actually tetragonal, so the films that go on top, up to a certain thickness, are also tetragonal, so not really orthogonal. And so the crystal structure of the YBCO on top of the substrate is different from the crystal structure of bulk YBCO. And the oxygen will then be more disordered, right? But the Fermi surfaces will be more symmetric because it will be then in a tetragonal structure, and the nesting features will probably also be enhanced. And that, this modification of the phenomenology may be favorable for the formation of three-dimensional charge order. So there's a lot of things to do, in particular with the strain device, where we can now do simultaneous diffraction and transport experiments, etc. And there, that's the cleanest realization of charge order that you can imagine. It's really three-dimensional long-range order, and it will be very interesting to see how it will affect the transport properties that we all know about. Okay. So I think I'm out of time, so thank you very much for your attention.
Thank you, Bernhard. Question from student Bernhard first. So left gentleman.
I have a student like
Yes.
So,
Well, these are the worst things. Worst questions.
it's very unusual that the 2D and 3D charge orders have identical behavior insofar as Q vectors in plane. And the only difference is in the Q vector in the Z direction and the range of correlations. Is that correct?
Well, okay, so there's one more difference that I didn't highlight, which is that the 3D charge was really uniaxial, right? So you only see it in one dimension. Okay?
In plane also.
Yes, in plane.
So that's like nematicity. Or you think this is already an orthogonal?
No, it's not nematicity because it's really translation and symmetry already. So it's a real.
No, I understand, but you're also picking up. It's also breaking C4 or something.
It's breaking C4, but okay,
But
for
it's
long
not-
I would say, the C4 is already broken by the crystal structure,
Yes.
by the chains. And so this is not really what you mean by nematicity.
Okay, I see. So, but there is also evidence for nematicity in IBC.
Yes,
Unlike-
well, okay, so that's maybe not completely unrelated, but so we have published evidence of nematicity from spin dynamics, which should be certainly much less influenced by the chains. Right? So as far as the spins are concerned, they all live in the planes. There's no active spin dynamics on the chains. So the spins ought not to be very sensitive to this minute orthorhomicity of the planes. Right? So there, we have always thought of the orthorhomicity of the crystal structure as a small aligning field. Right? So again, it's not a true nematic in the sense that the symmetry is already broken, but for the spin dynamics, we still think it makes sense to think in these terms. Right? Where the uniaxial anisotropy that appears more or less spontaneously in the spin dynamics alone. Well, now it turns out in the previous sample going to superconductor temperature, that can be thought of as a nematic transition.
So there is no sense in which the 3D order in a magnetic field is the 2D order becoming long range in 3 dimensions.
Well, not in a straightforward way, because then it would steal intensity out of the 2D rod, which it doesn't. Right? Both are actually enhanced. So, in some sense, there's certainly some kind of relationship between these two orders, but it's not like so you have these patches in the planes, and they just start communicating and extending. The correlation makes sense. Not there must be regions in the planes that are not really affected by neither 2D nor 3D charge, that then are converted to 3D charge at high fields or at high speeds.
Cheers.
So this beautiful epitaxial tetragonal YBCO, what is the termination layer on the surface of the crystal?
We have not studied that. Because our techniques are not surface sensitive, they're really bulk sensitive.
I'd be very interested to know.
Yes, so we have very nice and clean films now. Not IPCO, but DIPCO. They can be grown by MBE. And so we know, we have a lot of information about the crystal structure, not about surface properties, but yeah, maybe we can find out together.
If you make the comparison with another compound like charge-sensitive wave superconductivity equations,
okay, so yes, I can make a comparison, but it's I think the analogy is limited because with a solenoid, it's a multi-sheet film surface, and as far as I understand, superconductivity is really living on different charge density is living on different film surface sheets. So the interaction between the two is by far weaker than cuprates, where everybody's competing to the same states.
You see the same kind of peaks in the critical temperature.
What do you mean?
I mean, the amplitude of the charge modulation might also peak at critical temperature, for example.
Yeah, actually, it just turns out that many years ago, before we knew that charge was present in cuprates, we've actually studied urine dosilamide under high magnetic fields with exactly this question in mind. Is there interaction between like Steve? He saw this charge density wave peak, change intensity at the critical field. Nothing happens. So there was we actually published this as a null result of this with B. There's no anomaly of the charge density wave refraction at the critical fields of the superconductor. So there's really minimal interaction between the two phenomena. At least not, we can't see anything that works with the function.
Well, in the practice, would you see less glimpses there are few features?
Perhaps they're just too subtle. But at least at that time, we couldn't see. We didn't have very high magnetic fields, 10 Tesla, so.
Other question? So let's thank Bernhard again.